Hello everyone again and welcome to this particular video, and in this particular video here we're going to be exploring flux. And we know that flux is known to be the rate of migration of a specific property with the help of another property. Usually the other property is a constant, and another property as well is with respect to a specific derivative. So we're going to look at first what are the property that we are going to be focusing on based on our previous video, and then our next step is to be able to look at the transported property that actually relates to the property of focus. And then our next step is to look at how this property and the transported property relates to the flux, and from there we'll be able to analyze various units and the units that are connected in all these particular properties. And so first is looking at a particular type of property that we did on our previous video, which involves first looking at diffusion. And so looking at diffusion, we notice that diffusion is needing a particular transporting property which is called matter, and matter is actually used to introduce the flux. And so this particular flux linkage is known to be called the J in terms of the flux. So the matter flux is equal to the specific negative value of our D multiplied by the specific first derivative of another property, which is usually the number of particles with respect to our Z axis. And what we notice is that this D at n, or the first derivative of our number of particles, is showing a negative value, but the negative value decreases, therefore in terms of the integers. Therefore in total it is increasing as the number of flux, or the flux of matter, increases. Therefore, to make this matter flux to be positive, which is always greater than 0, we need to make our specific D to be negative. Therefore, this D actually connects really well with our diffusion, which is then used to analyze what our specific D is about. So therefore our D is determined by multiplying our 1/3 by our mean free path of our gas molecules, and this is multiplied by our mean speed of our gas molecules. So based on this particular formula that is used to determine our coefficient of our diffusion, we can then use this coefficient of our diffusion to analyze various relationships like the pressure, like the temperature of our system, and that is what we did in our previous video. So take note that since our matter flux is measured in terms of units to be equal to our number of particles per meter squared, which is the area, per second, in this case, we notice that in this part, our coefficient of diffusion in terms of the unit is shown to be, in this case, meters squared per second. So that is how you're able to summarize our specific diffusion based on the transport property, which is matter. And on our next part, which we talked about on our previous video, is looking at another property which is called the thermal conductivity. And the thermal conductivity is a property that will be requiring a particular transporting property which is called energy. And so the energy is important because we need to see how particles move energy from one region to another, and based on this energy movement we can use the energy flux, which is represented as J at energy, to be equal to the same constant, but this time it is a negative value and is represented as this weird looking K, and this is equal or multiplied, sorry, by the temperature first derivative divided by d at z. So take note here that the thermal conductivity highly connects really well with our specific energy flux with this particular constant, which is represented as K, and so the coefficient in this case of our thermal conductivity is equal to 1/3, and this is multiplied by our mean free path multiplied by our specific mean speed, and this is multiplied by our specific heat capacity of our gas at the constant volume, and this is multiplied by our concentration of our gas. Or you can use C, which is our mean speed multiplied by specific heat capacity at constant volume, all divided by 3 multiplied by square root of 2, and this is multiplied by our cross-sectional area and the number of particles of focus. So there are two ways to determine the thermal conductivity coefficient of our system, and based on these two ways we can derive our unit based on this particular coefficient of thermal conductivity. And so to determine the unit, we did this on our previous video, and based on our previous video we determined our unit for our thermal conductivity unit to be in joules per kelvins per meter per second. And on the other hand, based on our energy flux, which is what we talked about also in our previous video, the unit of our energy flux is shown to be in terms of our joules per meter squared per second. Usually energy or any form of property flux is a specific quantity divided by the area per second, and so that is rightfully shown right there. And finally, hopefully we have space for this, we have our next one, which involves looking at another property, which is the final property of our series, which is looking at viscosity. And the property viscosity is not only applicable to gases but also liquids, but it's quite different. We touched a little bit on that on our previous video. And in terms of viscosity, we notice the property that is transported is called linear momentum, which is usually on the x-coordinate or component, and the linear momentum is measured in terms of our particular flux, and the flux, which I'm going to abbreviate in terms of our linear momentum in the x-axis or component, is equal to our specific constant, which is also a negative value, and this is multiplied by the derivative or the first derivative of our velocity on the x-axis moving along the z-axis. So we have the x component on the z-axis that is actually showing this relationship taking place. So take note here that this relationship shows the viscosity relationship in here, and so therefore our viscosity relationship is shown as this particular variable right here, which is our constant. And so our constant can be determined in not 1, not 2, but 3, and the coefficient of viscosity is not only shown as 1/3 multiplied by our molar mass multiplied by our lambda, which is the mean free path, multiplied by our mean speed multiplied by our concentration of our gas, but also it can be determined by 1/3 multiplied by our mean free path multiplied by our mean speed. This is also multiplied by our mass of the atom and multiplied by the number density. And finally, it can be defined or can be determined by multiplying the mass of the specific atom by the mean speed, all divided by 3 multiplied by square root of 2, all multiplied by, in this case, the cross-section area. So all these 3 methods can be used to determine a specific coefficient of our specific viscosity. So the coefficient of viscosity can be determined based on using any of these 3 depending on the situation that you find yourself in. And so in terms of the unit for this, our unit for the coefficient of viscosity is usually, in this case, kilograms meter or per meter per second, or this is shown to be 10 to the power of -1 of that unit to be equal to 1 porous. And we talked about porous, which is a form of a measuring tool used to determine the viscosity of a gas, and this is represented as P. And on the other hand, here in terms of the specific linear momentum flux, we can determine the unit in this particular case to be shown as the following. We have this particular unit based on momentum to be mass times velocity, but then is per meter squared per seconds. Therefore, by evaluating that, we'll be able to come up with the unit for our specific linear momentum x component flux to be equal to kilograms per meter per second squared. So that's about it for this particular video. I hope you found this particular video that connects our flux based on all the videos that we talked about, based on the property of diffusion, thermal conductivity, and viscosity, and how they respectively require transporting properties that are matter, energy, and linear momentum in analyzing various perfect gases behavior. So that's about it for this particular video. Hope you found this really informative. Please, to get more info and in-depth analysis, check out our previous videos. By that way, you can be able to be well informed on various interesting behaviors and relationships that gases exhibit. All the same, stay smart as always and believe in yourselves.